Hey folks, I got an example with you. Again, finally plug some numbers in a calculator. This example is looking at the electric field between the parallel plates. So you're probably going to need a minute to copy the picture down. So go ahead and pause the video and take a moment to copy all that stuff down. All right, hopefully you've copied everything down. So we have a positive plate on the left and a negative plate on the right. Those are producing an electric field that points to the right. I've drawn a couple representative lines for that field. And we are going to move from A to B to C to D back to A. And each of those distances is going to be 4 meters. Okay, now by the way, this thing is not drawn to scale. Imagine the plates are really big compared to 4 meters. So the electric field's constant in there. The plate charge density, the amount of charge on each plate is, the density is 17.7 nanocoulombs per meter squared. The charge we're going to move around is 1 millicoulomb and is positive. And let's say its mass is 1 gram. Okay. All right. So for all of these paths, we're going to determine each part of the path. So like we're going to start by going from A to B. And we're going to figure out what change in voltage is, what change in potential energy of that charge is. If we need to, how much work do we have to do on that charge to make it move that part of the path? If not, was there a change in kinetic energy? Did it speed up? Like for instance, if you drop your pen, it's going to speed up and gain kinetic energy. So that's what we're looking at. And then in that case, what's the velocity of the little particle at the end of the path, that part of the path? So let's start from A to B. Okay, so if I push or move or let the charge go from A to B, okay, well, what is the change in voltage? Okay, well, change in voltage is negative the integral of E dot ds. Now, in this case, we're not going to have to integrate because the electric field's constant, right? So it's just negative E times the ds, all right, or delta S. Okay, now, when I go from A to B, we're going with the field. So this dot product is positive, but there's a negative out front, so our change in voltage is negative. So this is negative, the electric field. Oh, well, what is the electric field? I didn't give you that, did I? Okay, so we have to do a little calculation of that. Well, you might recall from the last chapter that a single plane of charge makes an electric field of sigma over 2 epsilon naught. If I have two oppositely charged plates of charge, let's see, the left plate would make a field strength of sigma over 2 epsilon naught to the right, and this negative plate would also make a field of sigma over 2 epsilon naught to the right. So combined, they make a field of sigma over 1 epsilon naught. So let me write that down to the side here. The electric field strength, okay, is equal to sigma over epsilon naught, which is 17.7 nanocoulombs, which is times 10 to the negative 9th coulombs per meter squared, divided by epsilon naught, which is 8.85 times 10 to the negative 12th. And if you do this, you get 2,000. And we'll use the volts per meter, okay? Because I picked a number here. This is 2, right? And then this is 1,000, so it's 2,000 volts per meter. Okay. Now, so now we have something to plug in for E over here, right? So this is going to equal negative 2,000 times S, which is 4. So this would be negative 8,000 volts. Okay, so that's our change in voltage. That's the first of these things we're going to find. And that's going to be the most effort to find. By the way, everything else will be pretty quick. Now, before we do that, before we do anything else, I want to make one more note here. For change in voltage, you can kind of think of voltage as an electrical height. So imagine that these field lines, they go from high to low. It's like water flowing from a high to a low. It's not the same thing, but it's an analogy that works okay here. So you have water flowing from high to low. So when we go from A to B, we're losing electrical height. We're losing voltage. Okay, so that's another way to think about voltage. It's kind of like an electrical height. All right, now delta U. Okay, well, delta U is simply equal to Q delta V. Okay, well, Q delta V Well, Q is 1 millicoulomb. That's 1 times 10 to the negative third. And if you multiply that by negative 8,000, you get negative 8 joules. So this little charge lost 8 joules of potential energy. In other words, it's falling from A to B. If you let the little positive, if you let the little positive charge right here, here he is right there. If you let him go, he's going to accelerate toward B all on his own. Okay. So how much work did that take to do? Well, it didn't take us any work to do. The charge will do it by itself. It's like dropping a pen. It'll fall by itself, right? How about the delta kinetic energy? Well, if the particle is losing 8 joules of potential energy and there's nothing else going on, then the change in kinetic energy will be positive 8 joules. In other words, it's falling and it's gaining kinetic energy as it falls. And then finally, what's the velocity of the particle? Well, velocity is the square root of 2 times the kinetic energy over the mass. So your velocity is root 2 times 8. Now the mass is 1 gram, which is 1 times 10 to the negative third kilograms. You need this to be in kilograms, okay? And if you do that calculation, you get square root of 16,000, which in my calculator gives me about 126 meters per second, okay? So when the little particle gets to point B, he's going 126 meters per second, okay? And then we're going to hold our hand out and boom, stop him, okay? So now he's stopped, okay? Now we had to do work to stop him, right? We had to do negative 8 joules of work to stop him, okay? And now we're going to move him from B to C. Okay, so what happens when we move him from B to C? Okay, so as he goes from B to C, oh, that's not a vector. As he goes from B to C, what happens? Well, if I do delta V is negative E dot delta S, well, E is to the right and delta S is down. What's the dot product? Well, there isn't any. So our change in voltage is 0, okay? Which also therefore means his change in potential energy is 0, which means the amount of work you had to do to move him from B to C is nothing. He's not going to gain any kinetic energy or anything. So that brings me to another point I want to make here. B and C are at the same voltage. The change in voltage is 0, so they're at the same voltage. They're not at 0 volts, but they're at the same voltage, so there's no change. So from B to C, well, we call that an equipotential surface. So in this case, okay, that surface is parallel to the plates. It's perpendicular to the electric field. Okay, so this blue thing I've just drawn is called an equipotential surface. All right, that means the voltage everywhere along that surface is the same, which means it doesn't take any work to move a charge anywhere within that surface. It'd be kind of like if you were rolling a ball on a level floor. It doesn't take any net work to move it from one end of the room to the other. You have to do a little positive work to get it going and a little negative work to stop it, but the overall work you do is 0. Yeah, it's the same thing here. So that's kind of like our level floor for our charge. All right, and then if we go from C to D, okay, what's our delta V there? Okay, well, there we're going against the field. So if I do my dot product, you're going to get a negative, but you also have a negative out front. So you're going to have 2 negatives, you're going to have a positive. So it's the same number, it's 8,000, but now it's positive 8,000 volts, which means delta U, which is Q delta V, is positive 8 joules. In other words, you're lifting the charge up. We can think of it to a higher electrical height. So the work I would have to do on it would be, I'd have to do 8 joules of work to get it to go from C to D, and there wouldn't be any change in kinetic energy if I'm just moving it at a constant speed from C to D. Now, by the way, before we do the last segment of this here, well, actually, I'll do the last segment. And what if we go from D back to A? Okay, well, if I go from D to A, you're moving perpendicular to the electric field, so you're not changing, you don't have any dot product here, so your change in voltage is 0 and everything else will be 0 as well. Okay. Now, what would change in this whole problem if this were a negative charge that we were moving around instead of a positive charge that we were moving around? So if this were a negative 1 millicoulomb charge, what would happen? Well, for going from A to B, our change in voltage would still be negative 8,000 volts because there's no Q in here, right? That just depends on the location of that you're in the field. Where are you at in that electric field? But delta U would change. Because Q is now negative and delta V is negative, this would be a positive number, which means, hey, if I have a negative dude here, okay, he wants to move left. You have to shove him to the right, okay? So this would be a positive, okay, positive 8 joules, and you would have to do that positive 8 joules of work to get him to go from A to B. B to C would be the same, it's 0. From C to D, delta V would still be positive 8,000 volts, but delta U would now be negative 8 joules. And that means that the little guy would fall if you let him go at C, he's going to go to D all on his own. And then he would have kinetic energy of 8 joules when he reaches D, and you could find his velocity, it'd still be 126. So the numbers would all be the same, but the signs on many of them would change. Well, actually, not all of them. The works would be different, and the kinetic energy would be different because the charge is different. The 8,000 volts wouldn't change. The 8 joules, the sign of it would change. So again, you have to think about electric field and potential only depend on where you're at here. Potential energy depends on not only where you're at in here, but what it is you are. Are you a positive charge or are you a negative charge? So again, that's what makes some of this a little more confusing. Again, I'll reiterate, in a mechanical system, you only have positive mass. You don't ever have negative mass to worry about. But in an electric system, we have both positive and negative charge. So how they behave in the electric field differs in the direction. All right, I hope that video was helpful, and thank you very much.